Hi everyone, this is Krishna Malagapati, working as Assistant Professor in Triple E Department, St. Peter's Engineering College. In this video, we are going to see uh, full wave rectifier with RL load along with the freewheeling diode action. Right? Look at this. So these are the waveforms for RL load, R and L load, and we already seen this entire configuration in the last video. Now we'll see the extension of this RL load, and we have to discuss about the disadvantage of this circuit. So what is the disadvantage? So here is the disadvantage is, look at this. This is the positive half cycle, negative. Positive voltage we are getting, negative voltage also we are getting. And for the negative half cycle of the input supply, we are getting positive half cycle and negative half cycle. Means what? We are getting both positive half cycle and negative half cycle, but whereas the current is positive only. Increment, decrement, but it is positive. Due to that, what are the characteristics generally we can call? Look at this. When we take the characteristics like this, right? And this is my V, this is my I. Okay, then I am getting first quadrant operation due to the positive voltage, positive current. Positive voltage, positive current will give us first quadrant operation. But what happened during this period? Negative voltage means what? This is the negative voltage, and we are getting the positive current. Means what? Second quadrant. So with this configuration of power electronics, we are getting two quadrant operation. Two quadrant operation means what? So up to alpha to pi we are getting first quadrant operation, then pi to alpha next period for the next half cycle. This value we are getting second quadrant operation. But what is the disadvantage of this circuit? The disadvantage is very simple. When there is a negative voltage here in this output side, which will reduce as the total output available, average output delivered to the load. Average value is going to be reducing. Means due to that, what happened? The power electronic configuration efficiency is going to be reduced. So we have to enhance the efficiency of the this network, this configuration. So we have to avoid that disadvantage of this appearance of negative voltage at the output side. Okay, just we will see once the input current waveform. So input current waveform drawing here itself at the input supply. Okay, look at this with another pen. Right? During this value, what happened? T1, T2 conducting, right? T1, T2 conducting means T1, T2 conducting means we are getting input current, and output current. I think. So look at this. During this period, what happened? The current is flowing through source side also. During this period also, current also flowing through source side. We can say I naught equal to IS. I naught equal to IS. Right? This is for the power electronic configuration, fully controlled rectifier with RL load. So we have to eliminate the disadvantage of this circuit. That is what? Negative voltage of the output is going to be vanished. It is going to be reduced totally, zero values. How do you make it? If you make this negative voltage into zero values, like this, then the average output voltage will be increased. Hence, the average output current will also increase. Right? Due to that, average power delivered to the load increases, and then the configuration efficiency furtherly increases. That is my intention. That's why what I am doing is to this circuit, to the same circuit, I am going to add the one freewheeling diode. One freewheeling diode at output side. One freewheeling diode at output side. One. I am adding one diode. So which gives us a good operation. Look at this. Apart from the RL load, I am using one freewheeling diode at the output side across the output. Look at this. I am using one diode here. I am using one diode here. I am calling this as a freewheeling diode. I am calling this as a freewheeling diode. Let us see the operation how it is going on. Let us see the operation how it is going on. These are my waveforms, right? I want to skip this negative part in the output voltage, right? Same thing. Positive voltage is applied. So positive voltage from the input side is applied to the transformer. Due to that, what happened? So T1, T2 triggered together. T1, T2 triggered at alpha and allows the current to flow. Allows the current to flow. Therefore, we are getting current is like this, voltage is like this, builds up across the load. And for the positive half cycle of the input supply, this is the current path A, T1, RL load, T2, B to A. So the same current is flowing through both supply and load. That's why the current waveform for both output side and input side is only right. Then look at this. After this pi, what happened? Negative half cycle starts to conducting. As we know, there is a voltage across the inductor. Initially, it was stored some energy when the supply is available. So due to that, what happened? It's going to be delivering its energy when the supply is not available during this condition. Due to that, what happened? Current is entering into diode first. Current is entering into diode first. Since it is uncontrolled device, it is anode, it is cathode. Current is entering into anode terminal of the device. Hence, what happened? We can say it's going to be conducting, and we can say it is short circuited. You can say short circuited, very important, very important, listen carefully. So once it is becoming short circuited, as we know, voltage across short circuit is 0. As we know, voltage across short circuit is 0. Hence what happened? During pi to alpha period, this output is maintaining the 0 voltages. This output is maintaining 0 voltages. But what happened? Conduction of T1 and T2, conduction of T1 and T2 up to this point. And who will conduct this during this pi to alpha? Here there is a DFW. DFW means what? Freewheeling diode. Action takes place from pi to alpha, where the negative voltage is appearing across the output. That negative voltage is going to be clipped off by conducting one freewheeling diode, by connecting one freewheeling diode across the load. Hence, whenever the voltage across the inductor will provide the source for the network or so network configuration. Immediately, what happened? Current direction won't change. Only polarities are going to be changed across the inductor, and allow the current is coming like this. It will become short circuited. As we know, short circuit voltage is 0. Hence, the output also maintain the same voltage 0 value. Whatever the short circuit maintains, because these two are in parallel. These two are in parallel. So in parallel circuit, the voltage is same but current is different. So like that we are getting pi to alpha freewheeling diode conducts. Freewheeling diode conducts other than the T1, T2. T1, T2 are going to be stopped their conduction after pi. After pi to alpha, freewheeling diode conducts. For the negative offset, what happened? So this freewheeling diode conducts up to which point? Up to alpha only. Up to alpha. Why? Because up to alpha only this VL is greater than the VS. Up to alpha only VL is greater than VS. After that, what happened? The VL is less than VS. VL is less than VS. At that condition, VS is serves the circuit other than the VL. Hence, thereby what happened? There is no source at the output side. Is going to be stops its conduction, becoming open circuited. Am I correct? It's a semiconductor device. It won't conduct. It is conducting till the voltage is available across the inductor. Please mind this. It's very important. After that, negative half cycle means input serves the circuit. Till input serves the circuit. Here from after alpha T3 T4 triggered, and they are going to be conducting up to 2 pi. They are going to be conducting up to 2 pi. After that, what happens? Whenever T3 T4 conducting, inductor stores the energy because of supply providing the input providing the supply for the load. Am I right? Due to that, what happened? This inductor stores the energy whenever the supply is available till 2 pi. After 2 pi, what happened? It delivers the, so it's going to be serves the circuit, then immediately it is delivering the source, delivering the voltage, it's going to be losing its energy. Thereby what happened? There is a freewheeling of current here. There is a freewheeling of current. You can say diode is short circuited, voltage is 0. Hence we are getting like this. For the remaining cycles also we are getting output like this. I think you got the idea, right? Who will conduct during this 2 pi to alpha? Again freewheeling diode. Again freewheeling diode. So this is the freewheeling diode action. Am I clear? Am I clear? Look at this. Right. So what about the voltage across? What about the voltage across T1 and T2? So whenever the T1, T2 conduct, short circuit, voltage is 0. Short circuit, voltage is 0 till this point. After that, what happened? So you are getting negative half cycle. You are getting negative half cycle. Then here also same thing. So from this point, you are getting negative half cycle. Now the waveforms been changed, right? And coming to one more. So now what happened is, during this period only, input having the current as same as the output. Now what happened is, input wave is being changed. Input wave is being changed. I am just drawing this input wave like this. Till the pi it is there, current is there through source. After that pi, what happened? There is no current flowing through the input side. Means what? Supply current is going to be 0. Then after what happened? Again you are getting current. Then after you are getting current till 2 pi. Again 0. Then you are getting current. Again 0. Like this you are getting current. This I am saying that this is 0 and this value is 0. Got my point? This is input current. This is input current. What about current flowing through the freewheeling diode? Current flowing through the freewheeling diode is taking a current flowing through the freewheeling diode is nothing but this portion. So this portion, right? How do we draw this? It's not possible to draw here, but you should remember current flowing through the freewheeling diode is like this. Okay, it's very important. Is same as one more information is that it is operation of R load. Simply, whenever you connect one freewheeling diode across the load for the RL load, then the entire operation which it is giving is the fully controlled rectifier with R load. We already discussed that in the last class. We'll see the expressions for this. First we'll see the expressions for RL load, then we'll see the expressions for RL with the freewheeling diode action. Clear of this? Right. So this connection is very important to analyze the RL load, and RL load is same as the R load if you are connecting one freewheeling diode across the RL load. First we'll see the average output voltage. Average output voltage. What is the equation? Average output voltage equation. It is V naught equal to 1 by T integral 0 to T Vs d omega T. This is the common equation that we are using for average values calculation. Then I am writing here, this is 1 by pi because it's repeating. So 0 to, sorry, it is not 0, it is alpha to pi. Alpha to pi, conduction takes place alpha to pi. we are taking, if you are going for RL load, it is for RL load it is Vm sin omega t, Vm sin omega t, it is for RL load, it is for RL load. What will be this value? What will be this value? I think we'll write here Vm pi 1 plus cos alpha, if I am not wrong, it is 1 plus cos alpha 2 Vm by pi 1 plus cos alpha, right? Suppose if it is for V naught is equal to 1 by pi integral alpha to pi Vm sin omega t, it is for d omega t for RL with freewheeling diode, RL with freewheeling diode at load side. Then what will be this? Sorry, this is 2 Vm by pi cos alpha, then Vm by pi 1 plus cos alpha, right? That much difference is there in output voltages. Then when you see the current values, when you see the output current, take the output current, average output current, average output current I naught is equal to, first write down for RL load, that is 2 Vm by pi r cos alpha, it is for R load, right? Then we'll see the I naught for, this is Vm by pi r, Vm by pi r 1 plus cos alpha for RL and freewheeling diode. Am I clear? Right. If you want to go for RMS values of output voltage, means RMS output voltage, what we are writing generally is V naught RMS, that is under root, we are getting like this 1 by pi integral 0 to, so let us take directly this, okay, alpha to likewise alpha Vs Vm square sin square omega t d omega t under root. So after solving this equation with different trigonometric methods, we are getting one equation, right? So with this we can write RMS output current value, RMS output current, that is I naught RMS is equal to V naught RMS upon R. Very simple. Once you got this equation, it's very easy to write the equation for RMS value. Right? After getting this, is these two are for the, this is for RL load. This is also for RL load. When you're going for RL load plus freewheeling diode, you will get here only pi. You do it later. Then get the exact equation for this V naught RMS and substitute that V naught RMS in I naught RMS. It's very easy to go for the calculation of I naught RMS and V naught RMS. What about the input power factor, input supply power factor? Am I right? What do you mean by power factor? Power factor is the cosine angle between voltage and current. As we know, So there I am writing input power supply, input power is equal to output power plus total losses. Am I right? Output power plus total losses. This is the common equation when you are going for efficiency calculation in generally in electrical machines. So what happens in when you coming to power electronics? So these losses are going to be I am taking as a negligible values because only we have the switching losses. Due to that I am taking this all things are 0. Then I can write this one is VRMS, IRMS, cos phi. Am I right? VRMS, IRMS because it is AC at the input side we have to take VRMS, IRMS, cos phi. Output side it is output side V naught RMS, I naught RMS. We have to take because it's not a pure DC at the output side. Generally, we are expecting pure DC at the output side, but it's consisting of a huge amount of harmonics at the output side. That's why we should take when we are going for like this, we should take the equal level values. V naught RMS and I naught RMS is equal to V RMS I RMS cos phi. So this is the thing we have to take into consideration. Cos phi is equal to V naught RMS, I naught RMS upon VRMS, I naught RMS. This is for I am calculating for RL load. This is for RL load. Mind it. Then what happened? These two are similar, right? Because look at this. These two are similar. I naught IS I said. Here what happened? Cos phi is equal to V naught RMS V naught RMS then VRMS. When you know these two values, then you can get the input supply power factor. Generally, what happens is it is RL load, cos phi is around 0.62, 0.62, 0.8 lagging, 0.62, 0.8 lagging, right? Please remember this. Okay, and then we discuss about this. The summary of this single phase fully controlled rectifier with the RL load and freewheeling diode is very simple. Whenever because of disadvantage in RL load, we are going for a connection of freewheeling diode across the load because the average output voltage is being going to be reduced when you connect RL load only because you are getting negative value. So we have to clip this negative value when you have the RL load by connecting one freewheeling diode. At that time, what happened? We are trying to boost up the output voltage at the output side so that what happened? Output power delivered to the load is being increased. Hence, we can say we can able to improve somewhat level the efficiency of the entire system. So that is the intention that we are placing the freewheeling diode. Once you placing the freewheeling diode, which indicates in what? Even though the load is a R load, if the circuit behaves like a R load. If the circuit behaves like a R load, then what happened? What happened? Very simple. We are getting only first quadrant operation than the two quadrant operations. Okay. So this is all about the single phase fully controlled rectifier with the RL load, and we have seen the configuration, circuit configuration. Then it's working out at what time the thyroids are going to be triggered and which are going to be conducting at what time, and the waveforms how we are getting based on the conduction of thyristors T1 and T2 for positive half cycle of input supply, T3 and T4 for the negative half cycle of the input supply, like so on. And we are seeing the freewheeling diode action, why we are using freewheeling diode and where the conduction takes place due to the freewheeling diode, what will be the output voltage. As we know, it is a unidirectional device and uncontrolled device. It conducts only for forward voltage. Once the current is entering into the freewheeling diode through anode terminal, which indicates what? It is the anode is more positive than the cathode of the freewheeling diode, hence it's going to be conducting and allows the current to flow you can say in generally that diode is a short circuit. That diode is short circuit means what? Short circuit voltage is zero. Because of the diode connected in parallel to the output terminals, due to that what happened is output also maintaining the same voltage value as same as the short circuit. So output voltage during that pi to alpha, during the whenever the prevailing diode conducts, it is also maintaining zero voltage. Hence we can say we are able to reduce the negative voltage at the output side. Then we can able to boost up the output voltage, average output voltage at the output side. Hence the power delivered to the load increases, system efficiency furtherly increases. So this is all about the single phase fully controlled rectifier. In the next video we will see some other power electronics device. Right? Any queries? No. Thank you.